It's a pleasure to be able to tell you about some of our work. What I want to discuss today is actually primarily on the three-body front. Will be the bulk of what I'll discuss, and the people involved in this particular project mostly are Jose Diancao, a senior research associate at JILA, Jia Wang, who did most of the real calculations I'll show, and Brett Esri. If I have a little time to talk about the five-body, I may skip four. But if we have time to talk about the five-body, Javier von Stecker carried most of this, this project. So I want to give, first of all, an overview of how we think about these problems. And there's a picture that goes back to even before my PhD work in the Fano group, where Fano started to evolve this picture that one could look at any reactive process whatsoever as simply a single coordinate of the system for a scattering event coming together in this one coordinate, one dimension, and going away off to infinity in one dimension. And every possible rearrangement or entrance channel can be described by a single size type coordinate called the hyperradius, which generally speaking is the moment, you can think of it as the square root of the moment of inertia of all the particles involved. So this was his concept, but implementing this has taken some decades to become reality for anything besides really the simplest few electron systems where he started this concept. But the basic math has stayed roughly the same since the early days in the 70s, before I really even joined the group. The idea is to generalize the Born-Oppenheimer concept and introduce one coordinate that you're going to treat as an adiabatic coordinate. In the Born-Oppenheimer concept, where it's the internuclear distance, it really is expected to be a slow coordinate because the electrons move so fast, they're so much lighter. In this context, it's not obvious that this is a slow coordinate and that it makes sense to treat the hyperradius as an adiabatic coordinate. But in a sense, this turns out not to matter so much because this can be formulated as an exact theory, an expansion into a complete basis set, as long as you really study carefully the convergence with respect to the hyperspherical adiabatic eigenfunctions. It can be made essentially exact. So the idea is to start, you're trying to solve this Schrodinger equation, like for a three-particle system. For j equals 0, it's a three-dimensional problem. You have a hyperradius, you have two hyperangles that sort of tell you the shape of the triangle with the three particles. And the logic is to first solve, to clamp the hyperradius, just like you clamp the internuclear distance. You clamp it and diagonalize the fixed R Hamiltonian and get a set of eigenvalues that are energies as a function of this coordinate. So we think of them as potential curves, just like in the Born-Oppenheimer context, these U nu of R's. This is a Hermitian operator, so the complete set of eigenfunctions are complete orthonormal and all that good stuff. So you can expand, in principle, the dependence of the wave function in terms of unknown radial functions and this complete set of phi nu adiabatic eigenfunctions. Then when you plug that in and project out the hyperangles, you get you've converted the partial differential equation in however many coordinates that was in originally. You've converted that to coupled, an infinite set of coupled one-dimensional ordinary differential equations. Okay, more than that, there is some physical insight you can get, for instance, by identifying the different channels in these potential curves with the different fragmentation or entrance channels. For instance, in this case, with three helium atoms, you have one set of potential curves that represent the three-body continuum states, and in the case of helium trimer, there is only one dimer state bound, so you get one potential curve going to the dimer plus atom channel. And so a recombination, which we'll talk about mostly here, means you come in from infinity on these one or more of these entrance channels in the three-body continuum. You make a non-adiabatic jump due to non-adiabatic coupling, and then you go off to infinity in the diatomic plus atom channel. And one nice thing about this is you can use these semi-classical ideas, Landau-Zener, or the generalization to Landau-Zener-Stuckelberg, and learn a lot about the system qualitatively as well as doing quantitative calculations. Now, there are many different ways to tackle the problem of getting the potential curves, and I think of this a little bit the way the way physical chemists think about molecules, in that, like if you go back to Mulliken, okay, he sort of said, well, the important thing is the potential curves. I don't care how you get them. I just want to get these potential curves and look at them and see the pathways and the bonding and all that good stuff. So, but you know, this can be difficult mathematically. There are a lot of details to be faced. So we have a whole range of different ways we'd use sometimes to calculate the potential curves. This one is what we have used. Seth Rittenhouse was in the group when we developed some of these methods. Uses basically simple Green's function ideas. If you go to the zero range limit of two-body interactions, then you can convert this to a simple integral equation and get analytically solve for the potential curves. And well, you don't have to understand all this math, but I just kind of wanted to show that it was there lurking. So when you apply that with the particularly interesting case of infinite two-body scattering length and zero-range two-body interactions, like in the sense of the Fermi pseudopotential, what you get is a 1 over r squared potential curve. This was derived by Efimov. This was his famous contribution around 1970, basically using different language, but in fact basically solving the same problem, just stating it differently in the context of nuclear physics. And the take-home point from this is that in this limit of infinite two-body scattering length, which from a mean field point of view is sort of the really, really strong interacting limit, you get this 1 over r squared attractive potential curve. Now, this sort of potential, if you think of it in a one-dimensional quantum problem that you might assign, you know, in a graduate quantum mechanics class, you can solve such Schrödinger equation with Bessel functions. They're a little bit weird. They have imaginary order. And for bound states, they have imaginary argument. But anyway, it's basically the same math that you would get for a charged particle interacting with a dipole molecule. You get also this sort of 1 over r squared attraction. And the energy level spectrum is analytically known. Successive levels go like geometric pattern. There are an infinite number of bound states. And there's a universal constant, this S0, approximately 1. In this particular case of 3 identical particles with infinite scattering lengths. There is this funny thing about this potential, which is the ground state is not really well defined, or you could say it's infinitely negative. It goes off to minus infinity, which is a phenomenon called in nuclear physics the Thomas collapse. Dating back to his work, I think in the 1930s. So yeah, this a disadvantage or feature, depending on how you want to think about it, basically unphysical, this Thomas collapse. It's always in nature, there's always something that changes the interaction. There is no system in nature known where the 1 over r squared attraction goes all the way to 0 distance. So somehow you have to fix the phase at some small but finite distance to reflect this physics, or change the potential to something more realistic. And these types of things amount to what is called in the Efimov physics or universal physics community, it's often referred to as fixing the 3-body parameter, is settling on what phase you come out into this 1 over r squared potential with. And that in turn controls the energy of the lowest Efimov state in the problem. In this infinite ladder, it's not infinite going to minus infinity, but it truly is infinite going to 0. Okay. So What we've been really developing, even dating back to my early work with Brett Esri and Jim Burke in the late 1990s, is trying to deal with these kinds of problems and not make these simplifying assumptions of exactly zero range. To, you know, if someone hands me a Hamiltonian for 3 particles, being able to really implement this strategy and solve the Schrodinger equation. So unfortunately, if you take, say, 3 alkali atoms, you get a horrifically complicated set of things, and it may not, at first glance, look like you've made any hopeful, promising progress by adopting this hyperspherical point of view. And you might think, well, I don't like all these channels, but the fact is, they are all there, okay? Every one of these channels here represents a different rho vibrational state of the diatom in the field that can fragment away in the field of an atom going away from it, with the whole system in J equals 0. So these are all real, and somewhere up here above zero energy are these 3-body continuum states, which are the incident channels for, say, 3-body recombination calculation. We were for years, really more than a decade, afraid to tackle systems like this with so many, 100 or more interacting channels, many close, avoided crossings, and many strongly diabatic crossings. It's a huge challenge to think of how to actually solve all those coupled equations and keep track of all this. However, there is a really nice way to handle this that was developed by Tolstik and Watanabe and Matsuzawa in the 90s, and we've recently implemented that, and it seems really stable. It's a really beautiful way to handle problems like this where you have lots of crossings. So we can, armed with this technology, we can go to more and more complicated scenarios that we think help to understand the richness and at the same time test whether 3-body physics really has this universality behavior such as the Efimov effect. Okay, so I already talked about this. Let me just go on to our first study in 1999 of 3-body recombination as a function of 2-body scattering length. At that time we were using sometimes other potentials, but most of our work was focused on this Sech-squared potential, which decays exponentially at large distances. It's very simple, and its scattering lengths are known analytically, so it was very convenient. And we found, for instance, that there are an infinite series of Efimov resonances. This is the first of an infinite series. The others are higher up at these universal predicted values from the Efimov factor, this e to the 2 pi over s naught. And we also found interference minima at positive scattering lengths. That's really the main characteristic that is important. At negative scattering lengths, you have resonances. At positive scattering lengths, you get interference minima. It took a while, but experiments caught up in 2006. This beautiful work from the Innsbruck group is really the first convincing observation of the Efimov effect. And they saw an Efimov resonance here, also at negative scattering lengths, as we had expected. They didn't really see the interference minimum, and although they saw actually a tiny minimum here, but it's not really visible on this scale, which may actually be connected with this effect. It's a little bit unclear even to this day whether we should interpret this little minimum here as essentially this minimum we predicted. But other experiments have since verified that this phenomenon of this minimum does exist at positive scattering lengths. So then there was an explosion, lots of experiments that basically bored on this problem and saw lots of beautiful results. Okay, so I don't want to bear on that because I want to get to the newest and most exciting developments in the past year. People were getting kind of self-congratulatory, like at a Rome workshop in 2009 when Efimov over here gave Randy Hewlett a high five for confirming some aspects of his early theories. But in fact, there was this bombshell paper in by the Innsbruck group in 2011, which kind of upset the whole apple cart because it seemed to violate some of the most fundamental assumptions of universal theory of the three particles in this low energy regime. And in particular, what they found was that this first Efimov state is not sort of going to randomly appear and you have to kind of have a random choice of this three-body parameter, which will probably be different for every three-body system. They found that, in fact, the first Efimov resonance is always at the same value of the scattering length if you measure it in units of the van der Waals length of interaction between any pair of atoms, any two atoms. It was always around minus 9.2, plus or minus 15, 20%. And this was a huge surprise to us and to, I think, almost the entire theory community working in this field. This is their physical review letter. Also had some theorists involved who were largely providing the two-body scattering lengths that you need to interpret the data that you see. And so this, let me just show you a little bit from their paper. This is how the scattering length looks, for instance, over about 1,000 Gauss. And they could measure 4 different Efimov resonances associated with four different Fano-Feshbach resonances. And this is kind of a funny scale, but basically if they all had the same scattering length of the Efimov resonance, the first Efimov resonance, they would all be equal. And you see more or less within error bars, they're virtually all equal. And the data was deduced from graphs like that, plotting loss versus magnetic field, and then turning that into loss versus scattering length. Then there was also a development in Gilla about this a little bit later, that they saw the same value coming out in a rubidium, a completely different atom. They also found that the first Efimov resonance, the only one they observed, is at minus 9.2 times the van der Waals length for rubidium. So in fact, when you look at all of the different Efimov states that have been observed, they all seem to fit this pattern from cesium, lithium-6 and lithium-7, potassium and 85 rubidium. There was really only one question mark, and it sounds like that question mark has disappeared recently. So this struck us as a question that we should really tackle and try to understand. And that's what we've done in the past year. We've really put a lot of effort into this, solving the three-body problem with 3 identical bosons, with many different interactions, trying first of all to see, do we agree that there is this universality that the experiments see? And the short answer is yes, we do see that. And then to see why. Why does that happen? And how universal is it? Would it be expected for nuclear systems, for instance? Okay, so the main finding, I'll set it in words here and I'll show you some of the evidence in a minute, is that there is a 3-body potential energy curve in this hyperspherical picture that has a universal repulsive barrier that we had not expected to arise. And it's there for every system. It kind of blew us away to see this. This is our preprint archive, and the PRL, which was in combat for a long time, has recently been accepted for publication. Thank you, Physical Review Letters up there in the sky, wherever you are. Here is a calculation that kind of shows the Efimov energy diagram that we get with doing, dozens, even hundreds of different 3-body calculations with different 2-body potential curves, or different 2-body interactions. All of the ones on this graph had a long-range van der Waals tail, but they handled the short-range physics differently in every case. So the black circles connected by the solid black lines are with a this potential, VA here, which is standard Leonard-Jones. It's written a little differently maybe than you usually see it, but it's basically a Leonard-Jones potential. But the different colors are different numbers of S-wave bound states in the potential. And you see they're just basically on top of each other. All these, which would have very different three-body parameters you might have thought, because the short-range physics is very different. For instance, when you have only one S-wave bound state, you don't get this huge spaghetti of zillions of potential curves. But as you add 3 S-wave bound states, you've also added several of D and G waves and so on, and you get very different looking potential curves. But all these look the same, and you can also put on other potentials. They're not on this graph, but they show the same basic effect. So here is, for instance, an example as we've tried to increase the complexity and really make this come closer to a real two-body interaction that has many bound states. So this is a case maybe where there are around 6 or 7, I think, two-body bound states, S-wave bound states, and many other higher partial wave bound states. All these below 0, all these thresholds, again, represent bound channels of the diatomic molecule. So when we blow up the region near 0 energy, in the energy region where we're interested in seeing recombination physics, we get the FMOD potential curve. This is at infinite two-body scattering length. You get the FMOD potential at long distance, and you see a barrier at small distance. There's this little blip you can kind of ignore that goes away when you diabetize the potential curve. There is an avoided crossing that makes that, but it's not so important. We go to the next pole, which means basically we increase the traction just to add one more two-body bound state, but we still have infinite scattering length. It gave this potential, okay? You still get a barrier at about twice the van der Waals radius. You can add a third, another bound state. It still has that barrier. It's very robust. Add a fourth. And all the way up to the 6th pole, you see that the trend that there is something that is not changing. There is a tendency for the three-body system to feel this strong repulsion when the atoms when the hyperradius of the 3 atoms is such that all 3 atoms are getting to a small enough distance that they would feel this interaction inside the van der Waals potential. Something, this barrier, is preventing them from doing that. The bottom line, when you calculate the three-body parameter in this form, this is the position of the first FMOD resonance, we call that A minus, divided by the van der Waals radius. You see they're all the values from many different calculations and 3 different types of potentials. They all fall kind of in this band, except the red that I'll explain in a minute is different. And these are the experimental points that fall in this band over here. So you see that we are pretty strongly confirming this universality, that there is a trend to have the three-body parameter, the first FMOD state, appear at around this value minus 10 or so times the van der Waals radius. The red, by the way, is a such squared potential. It has no van der Waals tail. And we converted it into this scale by equating the effective range to the effective range that a van der Waals potential would have. So we have kind of a fake van der Waals radius for the such squared potential. And you see when you make it deep enough, it sort of follows the same trend. But for the systems like nuclei that would have very few two-body bound states, it doesn't look like it's going to fit that pattern. So this universality of the three-body parameter is only maybe a quasi-universality. It appears it's not going to apply to nuclei. But for any atoms, 3 equal atom system, it looks like this is going to be a very general result, and experiments seem to be suggesting that strongly. They really discovered that. So now let me get to how we interpret this, what's going on. One thought that we had early on was that, okay, you've got this long wavelength. Every time 2 atoms start to come together at low energy, okay, they're moving in this complicated hyperspace, right? But occasionally they sort of come toward each other. but they're very long wavelength because they're very cold. They have a long de Broglie wavelength, and what they would see when they start coming together is like a cliff of attraction. It's like going over a hill, really over a cliff. And one phenomenon that happens in quantum mechanics with a very long wavelength as it encounters a cliff is it can be reflected back from the cliff. This doesn't happen as numerous scenes you've seen in movies. It doesn't really happen in classical physics. The car just goes over the cliff and it never bounces back. So we thought this might be, but when we actually calculate the de Broglie wavelengths to see if you're in this quantum reflection regime, it didn't seem to be. It looked like the quantum reflection, right, that this incident wave packet would turn around at this point instead of coming all the way in, turning around here and going back. It was really negligible. It never did that for this problem. So quantum reflection we basically ruled out, even though early on we thought maybe that was what was going on. However, our interpretation is more the following, that this cliff is still the controlling issue. And we know semi-classically that, right, the probability to be between r and r plus dr is proportional to 1 over the local velocity in classical physics. You know, right? If you're just screaming past a point, then you spend very little time in that region. And essentially the potential is just so deep. You can see it also in a WKB wave function. That's essentially what this 1 over root velocity of r is telling you in the WKB approximation. We've also quantified that in terms of a suppression parameter, which is integrating the wave function, the two-body wave function at 0 energy at small distances. And that shows this qualitative difference between the Sech-squared potential with few bound states and these blue and green, which are different hard wall or soft wall van der Waals potentials. There is a much higher probability to be at short distances in this Sech-squared than there is in this van der Waals or Leonard-Jones type potential. You can also see it from these three-dimensional graphs looking at the wave functions in the hyperangular space. This is the Sech-squared case, and these are the valley parts of the wave function where two particles are trying to come together. And the Sech-squared has a lot more amplitude in those valleys than the Leonard-Jones type problem. Okay, so it's kind of just like a roller coaster problem that you're just going really fast so you're not so sensitive to the physics at short distances. That's the words we're putting along with this numerical evidence from all these calculations. But you can see it in various observables. This is actually looking at the Efimov resonance in the three-body recombination rate. This is for the Leonard-Jones with 3 different numbers of bound states. You see the resonances all appearing at about the same place. You can also see it in the positions of the minima, for instance, on the positive scattering length side. Here for 2 different choices, 2 different numbers of S-wave bound states in the two-body interaction. So there are other universality things that are tested by this. We do see deviations from the universality predictions of Broughton and Hammer all over the place, but so it seems like you're often in the experimental regimes that are being studied to date, especially on the positive side of the scattering length. Your universality theory predictions, you're not probably far enough to rely on them real heavily. As a result of all of this, we could sort of make a summary potential curve because all those hyperspherical potential curves were going to one universal curve, more or less, with this one universal barrier at about twice the van der Waals radius.
Excuse me, what is the width of this barrier? Width of this barrier.
Well, I'm not sure what you mean. It's 1/10 of a Bohr or so, just from this figure. So, I mean, we have in our preprint and in the PRL to be, there is an effective potential if you want to use this and do your own calculations with it and experiment with it. There's also been some other work, theory attempts to explain this, one by Cheng Chin, which is kind of a back-of-the-envelope kind of a picture, and another by Schmidt and collaborator, which is on the archive you may want to look at. They have a rather different take on this problem, but I like ours. What can I say? I think I have time to say a little about 5 bodies. Okay. Okay, let's see. To go on beyond 3-body recombination, when Seth and Nirav Mehta were in the group, we had to think real hard, but we finally derived an n-body recombination formula. Basically, if we could calculate the potential curves, we could get the scattering matrix and all that good stuff, and calculate n-body recombination rates, which may seem a little weird because already you think it's a rare event for 3 particles to simultaneously come together and recombine. And we could derive sort of semi-classical versions of the rate coefficient that are kind of similar to the ones Broughton and Hammer derived using effective field theory for the 3-particle case. But it's a real interesting question how all this universal FMOV physics extends to 4 or 5 or even more particles. So, you know, much of the math is the same. It's just harder to get these potential curves. Javier von Stecker found a clever way using correlated Gaussians to do this for 4 particles. And found, for instance, here are 4-body potential curves, and found that confirming some other conjectures that there should be 2 4-body universal states that are kind of attached to every FMOV state. Okay, well, this is old news, goes back to 2009, but it's been confirmed experimentally. The 4-body resonance is right where this theory predicts it, and the implementation of the coupled channels to get the recombination rate even seems to more or less agree with the magnitude of the resonance. But what is newer that I wanted to talk about is trying to go beyond 4, which goes back to some work of Javier von Stecker by himself. He predicted that there should be universal states for 5, 6, 7, 8. He went all the way up to 13, a rather remarkable paper. And basically from this analysis predicted that you should be able to go to a negative scattering length where you can have 5-body resonantly recombine, but there is not yet any high-lying 4-body state. And you could go in principle to a place where 6 atoms recombine, but there is not yet the 5-body resonance. And so it's kind of showing the direction of going from few-body physics toward how clusters build up. It's really interesting work, I think. And he predicted these scattering lengths where you would see. So for instance, here's the 4-body resonance. I should maybe refer you to these values, which he improved in a physical review letter just this year. This should be 0.46 and 0.65 and 0.73 for the 6-body resonance. So this would imply that the whole n-body system is known once you've known the 3-body parameter. But now the 3-body parameter is known once you know the van der Waals interaction. So basically the many-body physics for these types of universal states seems to be fixed only by 2-body forces. Okay, so here is an experiment, and this is a paper we submitted jointly with the Innsbruck group that has shown evidence now for a 5-body recombination resonance. This is a schematic like one of their runs where they saw the 3-body resonance, the 4-body resonance, and now they see a hint of the 5-body resonance. When you really look at the loss versus scattering length, you see again the 3-body resonance, the 4-body resonance, and the 5-body resonance. No, I'm sorry, that's the 4-body, this is the 5-body. Maybe that's the 6-body, but they aren't claiming that yet. If you really try to put in the theory that has only the 4-body, it looks something like this. If you put in the 5-body additional recombination, it more or less accounts for this bump. And so we're pleased to report that this submission is not yet rejected by physical review letters. Cool. Okay, so that's where we stand. We think we understand the origin, why the three-body parameter is universal. I think there still could be other interesting angles to look at, like narrow resonances and so on, or multi-channel two-body resonances. A lot still could be done, but we have already started looking at the heteronuclear case where, for instance, you have two equal and one different atom, and it looks like that's going to be universal as well, but with a much larger parameter space. It'll depend on the relative masses, the different van der Waals lengths, and all that stuff. But it still looks like it'll be universal. We also saw a type of universality in the three-body parameter for three bosonic polar molecules, which have an Efimov effect as well. The challenge is there to see that first 6 or 7 body resonance. Some of you experimentalists in your vast spare time. Thanks for listening.